Hello guys, today we're going to be talking about PCB designing using DipTrace. So in this video I'm not going to be showing you about how you install DipTrace, but you just go over to their website, DipTrace, then you download the setup. Then after downloading the setup, you also download the 3D design so that you can view the design in 3D format after you've finished designing it. So there are a lot of various ways you can design your PCB, but the foolproof way is to first of all make a schematic. Then after the schematic, you go over to the PCB layout. Why this? When you make a schematic, there's a feature whereby you get what are called Ratlines, which I'm going to show you later in the video. Unlike if you've gone to the PCB layout straight, you end up with this feature of the Ratlines. So it's advisable to go to the schematic. Unless you are experienced, you can go to PCB layout. And as well, just going straight to the PCB layout, it's shorter and it saves time at the cost of making errors. Errors are higher if you go straight to the PCB layout without going through the schematic capture. So I'm going to click on the schematic capture. Then it opens the PCB layout, the schematic layout right now. So in this video, I'm going to be designing a small simple circuit, a microcontroller based circuit, whereby I'm going to be using a PIC 18F4520 with an LCD, then maybe just a few components like some LEDs and maybe a buzzer or interfacing a relay, that kind of stuff. So without wasting much time, I'm going to first of all place a component here, and the first component I want to place is the PIC microcontroller. So I go here on the components tab here. So I know that this component was made by microchip, so I go down to microchip right here, microchip. Then it's the PIC 18F4520. So I can scroll down to PIC 18F4520. There it is. Sorry, PIC 18F4520. I'm sorry, PIC 18F4520. Okay, there it is. So I know that is a dual line package. So right here you can also see the component layout. As you can see, you know that PIC 18F4520 is 40 pins. So you check right here the current format of it, because if you check another one like this one, this is the surface mount. We don't want the surface mount. We're going to be working with a drilled PCB. So you pick the one with 40 pins, then you place it right here. So as you can see, this is not the actual layout of the pins on the physical microcontroller. The first pin at the top left corner here is the reset pin, but as you can see, the reset pin is right here on the bottom, which is not the real case with the actual PIC microcontroller. So this must be taken in consideration. I always advise people to first of all download the datasheet of the microcontroller which you are going to be using and find the device pin layout. Okay, let me just bring it up. I think I have the datasheet right here, PIC 18F4520. Okay, so this is the datasheet of the PIC microcontroller. Now let's go to pin diagrams here. So as you can see, this is like the actual layout of the device, like in physical space. This is how the microcontroller is. The pins are arranged. So I always advise people to select the pins they want to use according to the physical layout, because you find out there are some people who would pick these pins right here, like RB0 to RB7, and as well pick pins right over here for a specific function, like say for LCD. For LCD, it's advisable to pick pins that are confined to the same region. Like here, if you want to use like for example the LCD in the 4-bit mode, you can just select pins RB7 to RB4 for the data pins, then maybe RB0 and RB1 for the register select and the enable pin. This will make a less complicated design. Unlike someone who picks pin RB7 through to RB4, then picks RD1 and RD0 for register selecting the enable. This will complicate the design, as you will see later. Why we always try to choose pins that are close to each other for a specific component, so as to lessen the constraints on the design, because you're going to find out that traces are going to conflict and they're going to intersect. So to prevent this from happening, it's advisable to go first to the datasheet and you see how it looks. Then let us go back to our schematic. Okay, so the next thing I'm going to do is I'm going to place my like the header pins, so that I can mount the LCD direct to the PCB. So for this application, I must have 16 pins like the LCD. Okay, so here I go to the discrete right here, then I go down to HDR 1 times 16, 1 meaning it's one row, then 16 means there's 16 pins. Okay, so this is the comment right here, like the header pins. Why I've chosen this, you'll see later. And there's also another factor. When you pick these components on the schematic here, you must make sure that they are the same. They have the same dimensions as the physical component, because if you just pick out of no reason, like you just pick because you feel like it is like the appearance of the pins that you want to, like if for example I click on this, you see this appearance as well. Let me look for another one like these ones. Okay, there's these other ones as well. But now here comes the challenge, like the dimensioning of the separation of these pins. You don't know it, but I've done the research before. Like our normal breadboard dimensions are 2.54 millimeters, and these pins are arranged in the same way. Like the separation between the pins is 2.54 millimeters, and this is the dimensioning of this HDR 1 times 2 pins. So we chose the 16 pin one. Okay, let me just reset. So to rotate it, you just left click on it, then you press R, or you can just right click on sorry, then you click on rotate, click on rotate again, click on rotate. So like I said earlier, we're going to be using port B for the LCD, so this must be over right over here. Okay, so I rotate this again. Okay, so from our LCD, we know that pin 1 is ground, right, and pin 16 is also another ground for the backlight of the LCD. Okay, so first, let me first of all bring all the components that are necessary, then I'll join them later. So the next thing we want is the voltage regulator. So okay, there's something I didn't show you earlier. So say you don't know like the manufacturer of the component, you can just go over to this binocular here, you click on it, then you click on all libraries, because you are going to search all over the libraries that are contained within the DipTrace. So you just tap, like we want the 7805 voltage regulator, 7805 voltage regulator, then I click on apply filter. So it's going to filter like the components here and filter off until the components which have the part name 7805 are remaining in this tab right here. So as you can see, it's still filtering is in progress. After it finishes filtering, the components which have this part name will remain here, like, as you can see. So we want the 7805. As you can see, this is the 7805. So before you design anything in DipTrace, make sure that you have like the working schematic, like a prototype, everything on the breadboard, and you know like the layout of the components in physical space, because here in DipTrace you just click right here. Like as you can see, this is another 7805. I click on it and you see it's a surface mount. But say you don't know like the actual presentation of the component in physical space, you're going to have a difficult time here. So it's always advisable that you start off with the components and you have them like where you are, so where you want them. So this is the voltage regulator. I just place it right there. Then we also want a crystal oscillator. Okay, the crystal oscillator is something that was difficult for me to find. Let me see if we can just get it by just searching for crystal, because it's difficult to find in this library. I don't think it's contained in this library. I might have to. Okay, as you can see, we don't have any pattern. Like over here, we don't have any pattern, so it's going to be difficult for us to work with them. Okay, that's fine. Let me just cancel this filter. To make life easier for you, I'm just going to leave this document at the link down below, or you can just comment on this video and I will send you the DipTrace file so that you can just copy my files. Okay, let me just show you how I go about this. Okay, I'm going to move over to a recent project. Okay, right here I've opened another circuit that I made, but if you can see closely, if I click on this oscillator right here, which is pre-made, like I had to make it. Okay, this is the attach pattern. As you can see, I had to like make the component on my own. It wasn't there in the libraries right here, but I think if you can search it, you can as well find it. Okay, so I'm just going to copy it. Okay, I right click on it, then I click on copy. Okay, I'm right back at the file which we're working on. Let me just paste the oscillator right here. This is the oscillator. Okay, so in order for someone to use the oscillator, we need capacitors. So go on components, discrete, you click on discrete, then we have these capacitors right here, and the 100 is just the dimensioning of the capacitor which you are going to be choosing. So the 100 one seems to be like the perfect size in our case. So all of this, like why I'm wiring the circuit this way, this is not something that we discuss like when we're making the PCB. Something that is predetermined by the circuit which you have made. Here I'm just showing you how you make the circuit into a PCB layout. We're not going to discuss like why is the circuit this way. I'm just going to show you how we lay out the circuit in PCB design. So so if you click, like as you can see here, if I go over to this box right here, let me just zoom in. Okay, this is the command right here, right? Then if I move my mouse to this point here, you see it becomes red, and I hover my mouse over. So the moment I hover my mouse over this, when I right click, it starts drawing like the wires, the electrical connections. So now say you don't have that facility again. We want us to connect. Okay, let me just move this to where we want it to be. So say you want to move this whole block, you just right click, then you drag and you select everything. Then you move your mouse onto one of the components you have been selected. You right click, then you can move the whole components. So this connects on pin that's RA6 and RA7 right over there. So let me just zoom in and you can show you. Okay, RA6 and RA7, that's there. Okay, so let me just remove this again. You right click on it, then you drag it down. So say we want to rotate this whole thing. If you click on R, see what happens. We don't want that. How do you go about it? We right click again, then we group the components, then we rotate them. They rotate as an entity. Then after rotating, we just ungroup them again. Then we're good to go. Okay, so we want to connect here, we just connect it like that. Okay, so the next step, we want to connect. Sorry, before we connect anything else, we want to add the necessary required components for this circuit to work. We have things like resistors, which we are going to have here. Then we have potentiometer for the LCD, so that we can vary the contrast. Then we have things like in our case, we may want to control a relay. So let us move over to relays here to add the relay. Okay, now here's the thing. Some of these components actually need to physically measure them. Like you actually have to select the component right here. You see the dimensioning, then you check the dimensioning of the component here physically to see if they match. Because if they have a slight variation, it means that when you drill your PCB, the component won't fit because they are different. I think that's obvious. So here I chose a relay that is called K something something, and this K something something is not like the actual name of the relay that I had. The relay that I had was called NT722S10. It's not right here in this library, but there's a relay with the same dimensioning as that one. Okay, let me just go back to that other schematic file whereby I already have the things. Okay, there we have it. Let me just copy it. There it is. Then I just copy it. Then I'm going to move over to our design. Okay, so let me just filter and search for that name. I apply filter again. Okay, as you can see, there is the relay, and this is the actual relay that I have. Okay, there we have it. Then I can just come and place it right over here, and I cancel that filter. Okay, then I'm also going to need a transistor for the connection of the relay. In this video, I'm not going to be discussing about electrical reasons why things are the way they are. We're just going to be talking about how to design a PCB. Okay, so the transistor that I'm going to be using is called the 2N quad 2. I applied the filter again. So you apply the filter whenever you don't know like the actual manufacturer of the component, but if you know the manufacturer of the component, you can just go over to this components tab here and you can move over to their component. Like, okay, we have the transistor there, right there, then I have the transistor there. Then the next thing is the diode. I need the diode again, so I'm going to move to the top right there, then over discrete. Then as you can see, there's the diode right there. But if you want specific diodes like the 1N4007, again is also search. I don't know if it's there. Let's just search. I don't know if it's there in the libraries of the DipTrace, but let me just search 1N0041, the most common diode used. Yeah, there it is. Okay, so I just rotate it again, then I place it right there. Cancel filter. Then I'm going to need a resistor. So here the resistor values, they change. Like, okay, I'm going to show you in the PCB layer, because right in here they just have the same dimensioning. Like this is the RIS 400. Let me pick another one. You see, they just look like they're the same size, but as you can see right down here, this is 700, this is the 400. You see the dimensioning is changing, but when you put things in the schematic, you don't actually see that. So let me just remove this. I select them all, right click, delete. Okay, let's just pick the small one right there. Okay, so we're going to be having a relays part here. Then we're going to be having the LCD. Then we also need a potentiometer. So there are these common potentiometers which are used. Okay, I'm going to put a picture somewhere in the video after editing that I'm going to be using for this circuit that I'm designing. In the real physical space, the potentiometer will be in such a way that pin 1, pin 3, and pin 5 are the pins that are going to be utilized by that potentiometer. Like pin 2 and 3, they are not going to be used. Okay, so what's next? We also need a resistor. We need a resistor for pulling the anode, like for dropping the current to the LCD backlight. We use that anode. Okay, we also need capacitors to smoothen out like the DC transients, should there be any, from our power supply through our linear voltage regulator. So just 2 of them will be suffice, I think. So I'm going to choose random capacitors because most probably we are going to be using polarized capacitors. So I just put one in front, one in there. So okay, I think this is all we might need. If there's anything which we are going to be needing, we are going to add as we go on. So we are going to need the terminal block. Okay, some of these components I think I'm going to put some pictures so that you can see the actual component that I'm talking about. So for the terminal block that I'm going to show you in the picture is this part number here, 0. Okay, some of you may be wondering how I got to know this. This was after testing. Like I actually had to measure the components. I'm going to show you how you measure the components in the PCB layout. Okay, so this is the terminal block that is the same dimensioning as the one I'm going to be using. I'm going to show you later in the video. So let us connect everything. Okay, so I'm going to skip this and show you the final connections of what we have apparently right now. On the relay here it may be confusing, but this is the coil and these are the contacts, the normally closed, the common, and the normally open. So your connections are made here for like the signal which you want to be turning on and off. And for energizing the coil, we energize this part. Okay. So sorry, this diode here must be connected between the coil windings, across the coil windings. Then they are as well connected to 5-volt supply. Okay, I'm going to speed up the video again. So I'm going to like rename these header pins so that you can easily follow through when you finish your PCB design and know what it means, like if you end up making a silk screen. So I'm just going to enter this component LCD, then this one is called the potentiometer, so I'm going to name it port. Then here I'm going to name it input. Then on the relay part here, I'm going to put another header pin. Okay, since the switch you may want to have a connection like it's normally open, then we turn it on using the microcontroller, then we have a connection from pin 2 to pin 1 right here. So I'm just going to name this switch, switch. Okay, so for this small video, that's all about it. For more complicated designs, I think having done this, you can move on to like more complicated design. So I'm just going to save this and let's just confirm. Okay, you now need to confirm like is all the connections where the ground is supposed to be. So from here I know that this pin 2 is ground, so I'm going to move over all of the circuit and see if it's where it's supposed to be. Like the ground, I know that the microcontroller must have a ground, the transistor must have a ground, and apparently the microcontroller has 2 grounds. Then the oscillator is a ground on the capacitors. Then my potentiometer is a ground. The LCD has 3 grounds. Then I move over to the supply. As you can see here, we don't have a connection here, which must be there. So I must correct that. Move over to here. Then I click. Okay. All right. So now we have a connection. Then this is the ground. As you can see, the ground, we have connection throughout. Then from the input power to the input of the regulator, we have a connection. Then our 5 volts. Then again, I know that my 5 volts must go to the relay conduct and the diode. Then 2 pins on the microcontroller, on the potentiometer, the relay, the LCD. Then the anode of the LCD through a relay. Yes, those are the connections that are needed. So I save. Then after this, we are done with the schematic. We can now certainly go over to the PCB design, and the PCB designing will be easier since we have an added feature which I'm going to show you. So you can just hit Ctrl B, or you can go on File here, then convert to PCB. Then it opens the PCB terminal. So if you've designed an earlier PCB, you can just use the rules and schematics of the previous layout. But maybe I'm assuming that this is your first PCB design, so you just use the schematic rules since you don't have this file. But say you get my file that I'm using, you can just click on this one, then you browse and select this file that I've made. After I've made the PCB, then use that file. But considering that maybe this is your first, you're just going to use this one, use schematic rules. Click on OK. So why was I saying this is a good idea? As you can see, we have this feature now. These are called Ratlines. We show you where there are supposed to be electrical connections. Now say if you've just moved over to PCB here and you don't have these Ratlines, you're going to manually do see where the connections are. And as you have noted from our earlier schematic, there was an error there whereby we thought whereby I thought I had a connection and the connection was not there. Now imagine after completing this PCB design and think there are connections all over, but there isn't a connection. Now these Ratlines, they are there to show you that is there a connection or not. Okay, so there's also another feature why I wanted to why I picked this component here, which is the HDR 1x16. Okay, let me show you the measuring. Right here, just on the right of the cursor, with this measure icon, you select this measure tool. You select on the center of the pin, then you go to the center of the next pin, right there, and the length is reflected 2.54 millimeters, which is the standard distance between the pins of a breadboard, which also is the standard of many of the components which you use, the LCD, the pins of the microcontrollers, the potentiometers, like in this case the potentiometer which I'm using. Okay, so now we need to place the components. Here comes another issue where most of people need help with. When you get to this point, you must make sure that you have arranged all the components in a way such that the traces do not like get mixed up. Let me show you what I'm trying to say. Let me move this over to the side and move this microcontroller here. As you can see, let me rotate this. The ideal way will be putting this way, because as you can see, like we have direct connection from the microcontroller without any complication. Now you see someone who has their LCD here. This is going to complicate the routing process, because we are saying you're going to move from this path going right here to this path going right here. So this is where a good designer makes most out of this software. You just need to place the components where there's a lot of convenience for the design. So the crystal oscillator again here, as you can see, I must rotate in such a way that there's less complication. Like now you see we have direct connection from this pin, and like here whereby we have this crisscross. So I just rotate again like that. Then I bring over the capacitors. Then the capacitors as well, they need rotating. This one must be here, the other one right there. Then again, as you can see, we have this pin is connected here, but it's not the pin near to this pin, so I have to rotate it again. As you can see, we have direct connection, we have a clear connection from the, again we have the same situation here. Then I do the same again. Then I move the pins closer. Okay. Then I move the potentiometer closer to the LCD. Then we have the resistor for the backlight. Let me just rotate it. Okay. Then we have the input. Then for those who are more interested on why we are placing the components where they are, we have a PCB lecture PowerPoint that you can just ask for and I can give you, and you can actually understand why we're doing some of these things, like why is the power here. There are design rules why we do this, like sections which are having the same functionality, like for example power circuitry must be confined to a specific location. You cannot have your power components spread all over the PCB. That is a bad design. And as well, there are things like heat sink placement and so forth. So as you can see, this is the voltage regulator, and if you have noticed it physically, we have these two lines here. These two lines represent the back plate, whereby we have the ground plate, that metal flap. So when you're mounting your heatsink, you mount it right here. So that's why I'm leaving this space in case we want to mount the heatsink. Because if I have this capacitor right over here, it's going to complicate it. So I just move the capacitor right back there, and maybe this one I can move it closer because nothing's going to be here. Okay, next thing, let me put my relay there. I rotate this resistor so that pins connected to each other are closer, adjacent to each other. Then I move this so that we have a very small PCB. Then these components must come here. Okay, then let me just rotate this. Okay, right there. Yeah, actually move this over to there. Then the switch can be right here. Okay. Now I'm just refining things so that we have a very small PCB, and this can also be done after you have routed the PCB. But it's usually a good design principle to first of all arrange the components the way you want them to be. Then after routing, if you discover that the traces are having a lot of trouble, you're having a lot of trouble in getting traces that are not intersecting, you just then space the components out. So afterwards, we want to press a board outline, which is this tool here. Then I go over to this corner, then just select that corner and you move around until you close everything in together. Don't mind about the shapes, you can refine this. So you go over back to this corner, you right click, both points. Let me move over this to the side so that you can actually see. So we want to create a rectangular board. The width, let me just make it 120. 120 is too much. This is the width. So let me put it at 90. 90 is too short. 100 too long. So I think let's go in the middle. 95. 95 seems to be sufficient. Then the height 100 too big again. I think 90. Yes, 90 seems to be sufficient. Then I click on OK. So after this, there are two ways to go about it. You can either auto route it, I don't know how you pronounce it, route or route. Then you auto route it, or you can manually route it. So it all depends with the time you have and how you want the circuit to be laid out. If you're a very good PCB designer, manual routing is the best because you already know how to route things. But if you are a beginner, I strongly suggest that you auto route this. Then after auto routing, you can adjust manually, and it also saves time. Okay, so there are some steps you have to take when you want to route. Now, before I forget, okay, I'm going to show you later. It's about this transistor over here. I'm going to show you later. Now, we have to set up the routing parameters. Now, say you want to, like considering this circuit, this can be one-sided circuit. You don't have any complicated components right here. So we are going to make it a one-sided PCB. So you go over to the route here, then you route setup. Then on setup, want the trace width, you can just leave the trace width right here, 0.5 millimeters. Then the trace width separation, again 0.5 millimeters. We can as well change this later. I'm going to show you how we can do this. Then settings, I think that's all fine. Then you click on OK. Then go on route again, layer setup. Okay. Now layer setup is where we define whether we want our PCB to be two-sided or one-sided. So we have the top here, then we have the bottom right there. So apparently with the top. Now the top we want our traces to be on the bottom. So the top you make it a plane. Then just close. Then the bottom it remains signal. Then you close. That's enough. You go back on route, then you run the auto router. So as you can see, because this is the top side, so to move to the bottom side, you just click 2 on your keyboard, or you move over here and select the bottom. As you can see, just because we had positioned our components in a clever way, that's why we are not having any traces which are conflicting, and you don't need to have any jumper wires or anything. Let us now refine these tracks, because like I was saying earlier, refinement is needed. And for some of the reasons why these things are changed, you actually need to view that PCB lecture that I was talking about earlier. Okay, so we now want to refine, and this is where you actually discover who's the best designer and all that stuff, because it's reflected by how the traces are arranged, the spacing of the traces, and as well the quality of the component placing. Cancel. Okay, before I forget, earlier I said something about this transistor here. Okay, after you finish like etching the PCB and maybe you want to drill and solder, you discover that these pins are too close to each other. So how do you go about it to make sure that this error is prevented from ever happening, whereby you make errors just because the components are too close to each other? You can just replace this transistor package with a transistor package of the same design but having bigger dimensions. So just right click on it, then you go to replace component. Then there's this component which I usually use, the 3724 right here. Then I click on OK. As you can see, apparently it has became larger. Then that's all you have to do, so that you make sure your components are not too small or anything. So now we want the traces to be bigger. Now we are going to be having a copper pole which is going to spread throughout this PCB. So this net here, which is net 2, we don't need to enlarge it because the copper pole is going to do that for us. So now I'm going to place a copper pole all over the board. There's this 2 here. On my screen it's a blue with a trace in between. So I click on it, then I just move over through the layout, making sure that I don't reach the edges. I leave a gap between the edge and the line that I'm drawing, the edge of the board outline. Then I click on OK. As you can see, this is the copper pole. Now I want this copper pole to be connected to the ground. How do I do that? From my circuit I know that the ground is this right here, and it's called net 2. I go back to my copper pole, I right click, go on properties, I go on connectivity, connect to net 2. Then this is going to make sure that this copper pole is connected to the ground. Then I go back to the pouring. Then I want the trace clearance to be 1, like the copper pole from the traces that are not the ground. I want there to be a clearing of 1 millimeter. Then I also want to remove islands. What are islands? Islands are just places where the copper pole is not connected to anything. Okay, let me leave this unchecked so that you can actually understand what I'm trying to say. Then I untick this again and click on OK. Okay, so this is the connection which has taken place. So from this you can see here, this ground is not connected to anything, this copper pole is not connected to anything. Now let me demonstrate the island removal. Unconnected, I click on OK. As you can see, we have removed all this. Okay, so it's up to you actually to identify whether you want to remove it or not. Now let's move over to the second step. Let me just unport this copper pole so that you can work with the OPCB, like the traces are easier to work with. Properties, then I go on unport. This unport, you just make sure that the PCB, like the copper pole will be there, but it won't cover the OPCB. And when you want to bake, just come here and click on port, unport, then you click on OK. Then now what's next? We want to select all the traces, right? Then after that, right click, then net width. I want to increase all the traces to 1 millimeter, right? They've all increased 1 millimeter. But remember, the ground we don't want to change it to 1 millimeter, as it's going to be covered by the copper pole. So I go back, I click on net width, I change it to 0.5 millimeters, just 0.5 millimeters will be fine. Then the whole net width is fine. Now say you have a trace, right? And okay, let me just show you right here. I just want to change this trace only, not changing the whole trace like we did earlier. I right click on the trace, then I click on net width, custom again, then I just 3 millimeters. Then you see it increases size. Then I do it again on this one, net width, then again 3 millimeters. It changes, right? Then let us just move things around so that we can see other features of DipTrace, because apparently we finished designing this PCB, but there are some features which are essential because PCBs come in various forms and sizes, and complexity differs from the PCB someone is designing. So how do you put a copper pole for a selected trace? Like the one I showed you first was for the whole PCB, but now I want to show you another copper pole, say for just one pin. Okay, let me do this first. Let us go back and restore the copper pole for the whole board. Okay, so say you have moved this trace right over here. See, we now have a DRC. Like there's a conflict. You can also check for this using the DRC. Like if we have a conflict right here, you click on DRC. DRC checks where they have a conflict. By double clicking at it, it highlights where the error is. Then I just close. Now this is because the copper pole is conflicting with this trace. This trace is a foreign trace to the copper pole. So I go back to here, I right click, then I click on update. What update does is like it changes the outline of the copper pole so that it can accommodate this trace which is moved by clearing it away from the copper pole electrical connection. Okay, so now I want to fill up this space with the copper pole, which I'm going to connect to this trace here. I go back to this 2 place copper pole, then I just start drawing here. And I draw okay, that is the copper pole. But now as you can see, it's not connected to anything, but I want to connect to something, and I want to connect to this trace like we did earlier. This is net 13. I go back to the copper pole, I right click, properties, 13, then I click on OK. As you can see, we've now connected this copper pole to this trace, and that's all about it. If you want to go about DipTrace designing your circuit and so forth. Let's just update this again. Then for things like screen printing, you go to this tool here, which is letters, place text. You click on where you want to place the text, you write what you want to write. So let's just write 4-bit LCD, 4-bit LCD, then I go over here. We want this to be the top silk, then that's all. You just now move it. You just now need to move it, and you place it where the component you want to display the text on. Then say you want to name like this controller that this is a PIC 18L4520, then I can just copy this text, then I place it right here. Sorry, paste it right there. Then I can move it right here or here, wherever I want to place it. Then I right click again, I click on this label, then I can just rename it to what I want to rename it to. In this case, PIC 18L4520. Then I click on OK. Then the text is right there. So okay, you want to resize it, you can just resize it by right clicking it. Then you move the cursor to the one of the corners. As you can see, it changes the cursor to this resize to. Then you can just resize it whichever way how you feel. Then say you want your PCB to have like drilled holes or what, there's a tool right here, place mounting hole. You take it, you just place it right there where you want it to be. Okay, this is the mounting hole, right? Then I can just define the properties, like I want the outer diameter to be, just right click on it, then you go on properties. Then I want the outer diameter to be 5 millimeters, the whole diameter to be 4 millimeters. Then I click on OK, right? Then I place where I want to be. Then I update the copper pole so that it does not go through the hole. Then I can just copy this hole again and then place it, paste it where I want it. So say I want to mount this on the on 4 corners. You can just do this. I place it right again there, paste again. Then move this to the corner there. Then afterwards I update the PCB. Okay. Then we have our 4 mounting holes there. Then we just want to check whether we have our PCB in the right way. Design rule checks for errors and what. Click on OK. Design rule check again. So now say you've made your PCB, but there are two traces which are conflicting. Say let me just pick a random trace that I can make to be conflicting with the other trace. Okay, say we have these traces. They are like this way. Okay, with these traces this way, they are conflicting, right? And there's no other way for you to ensure that they don't conflict. There's a way you can go about it. There are what are called jumper wires. So at this segment right here, I can just right click, then I go on segment layer, then top jumper wire. There's a top jumper wire there. Then I go on this segment right here, and I go segment layer, top jumper wire again. Then we no longer have any interfering traces. But in this case, that is not the case, so let me just put it the way it was. Okay. So say you are now routing. Let me go back. Let me just find a trace. Let me just pick a trace to route. Say you are routing from here, you're going there. Then you okay, let me go again. Sorry, let me just cancel all this and remove this copper port so that it can be visible. Unport. Okay. So say you're now routing right, you're routing. Then you want to route to this trace here, but you're going to interfere this trace. You can navigate your way out of this trace by going through this way, right? Then you get to where you want to connect. But now say you want to connect to this trace. How do you go about it? You reach here, then there's no way you can jump these traces without interfering them. Then you just right click again, you click on top jumper wire, then it moves the trace to the top using a jumper wire. Then you go there, then you continue your trace, then you're connected like that. So this is just an illustration to show you if you have a layout which forces you to do this. Let me just delete this, okay, and update this again. So that was an illustration to show you if you get to such a situation whereby you are forced to do that. But apparently, because we chose the pins of the microcontroller in such a way that it will be less complicated, that is why we ended up having this. So if by any chance that happens to you, because there are designs whereby you actually pick the right pins of the microcontroller, but just because the components are too many, they are going to be conflicting traces, and you are forced to go through the jumper wire method. That's still fine, but always try to make sure that you don't end up there. And I think that's all for this video. I know it's a very, very long video, but I think I have exhausted all the necessary things that are essential for one to make a PCB. Then okay, this is not really essential, but after I finish making a PCB, you just want to see how it looks in physical space, you click on 3D. Now this 3D aspect may not be there for you if you don't have the 3D models downloaded on your setup. You actually need to download the 3D models, install them in the same directory as the DipTrace file, as the DipTrace setup. Then you can have the 3D models. Okay, so as you can see, there are some models which are not there, but nevertheless, they are not like really essential for showing how the PCB layout looks like. There are some other components that are really essential. They are there already. Okay, so this is how the PCB would look like in physical space after etching it and so forth. Okay, so these components are missing, like the other pins and so forth, but they are the actual size. That's why we chose them. Then you have your regulator here, the capacitor there, then you have space here so that you can mount your heatsink. Then you have the terminal blocks, which I'm going to put a picture up so that you can see the terminal blocks which I'm talking about. So guys, there you're having your mounting holes there, 4 mounting holes, your diode, the crystal oscillator there, the microcontroller, capacitors, the transistor. So this is the way it's supposed to look like after you have etched it and maybe soldered. But as you can see, there are no soldering points here, but this is how it's supposed to look like in physical space. So guys, thank you for watching this video. I hope it has helped someone out there who wants to design their PCB using DipTrace or any other software which is similar to DipTrace, because PCB designing is just the same. The difference is that maybe the layout of the software you are using, the tool for designing which you are using, but the actual design essence is the same, because you can actually design the same PCB using Proteus. Maybe you can, the only things that can change are like how you get to use the copper pole and so forth, but the basic PCB designing is the same. So thank you guys for watching.